Welcome to Module 3, which covers Chapter 4 of the textbook, The Logic of Boolean Connectives. In this module, we've got four main learning objectives. The first is to compare and contrast the concepts of logical consequence and the more precise notion of tautological consequence. We'd also like to compare and contrast the concepts of logical equivalence and, again, the more sort of strict notion of tautological equivalence. We'd like to compare and contrast logical truths with tautologies. And then finally, the sort of most difficult and time-consuming process will be to recognize tautologies using the method of truth tables. So last week we introduced the notion of logical consequence. And as a reminder, we say that a sentence S is a logical consequence of a set of premises, say P1 through Pn, if it's impossible for the premises to all be true while the conclusion S is false. In other words, in any circumstances where the premises are all true, the conclusion has to be true as well. So this is just a rephrasing of that. And I'll remind you that that's one of the sort of key sort of goals of the course is to analyze this notion of logical consequence. At the moment, it's a bit imprecise, but in this chapter, we will introduce the notion of tautological consequence and of tautology, making some of these logical concepts that we've been talking about that are a bit imprecise a little more precise. Closely related to the idea of logical consequence is the notion of logical truth. And we'll say that a sentence S is a logical truth if it's impossible for the sentence to be false. A sentence that is a logical truth is also said to be logically necessary, meaning that that sentence is true in all possible circumstances. Now, a sentence that's true in some possible circumstance is said to be logically possible. Now, these two terms are vague in the sense that we haven't really said what a possible circumstance is. So in the next few slides and for the remainder of this lecture, we'll introduce some new concepts and some new terms related to logical truth, logical consequence, logical necessity, and logical possibility that are a bit more concrete and more straightforward to check. The first concept that we'd like to introduce that is more concrete than logically possible is the notion of Tarski's world possible. And we'll say that a sentence P in our blocks language, that's the one that is used in Tarski's world, is Tarski's world possible, or just TW possible for short, if it's true in some world that can be built in the program Tarski's world. In other words, you can construct a world file, and when you hit that evaluation button up in the upper right-hand corner, you'll get a true value for your sentence P. Now, it's important to realize that some logically possible sentences are not Tarski's world possible, but all Tarski world possible sentences are logically possible. So, in other words, one thing that counts for a possible circumstance is something like a Tarski's world file explaining the truth and falsity of each of the atomic sentences in the blocks language. On the other hand, again, some logically possible sentences are not Tarski world possible. And the book gives a really nice example of that you can see up here at the top. Here we've got the negation of the disjunction of tet B, cube B, and dodec B. Now, in Tarski's world, if we have some object that is being named by the constant B, then there are only three options for that particular object. It can either be a tetrahedron, a cube, or a dodecahedron. So that disjunction must be true in any world that you can construct in Tarski's world. And then the negation, remember, flips the truth value, and therefore that sentence would be false in all possible worlds that you can construct in the program Tarski's world. In other words, it's not TW possible. On the other hand, thinking of possible logical circumstances, perhaps we expand our world to include shapes other than tetrahedrons, cubes, and dodecahedrons. For example, we might have a second program, something slightly different, that allows for tetrahedrons, cubes, dodecahedrons, and maybe spheres. And if B was being named by a sphere, then tet B, cube B, and dodec B would all be false. The disjunction would then be false, and the negation would be true. And so, in that sense, if B was a sphere in this world, it would be logically possible for this sentence to be true. And so, again, this is an example of something that's logically possible, but not TW possible. So we've now seen that Tarski's world counts as a possible circumstance for something like a logical necessity or a logical possibility. We'd also like to introduce another method for determining when a complex sentence is possibly true or necessarily true. And that's the method of truth tables. And it's an extension of the semantics that we introduced for the Boolean connectives of negation, conjunction, and disjunction. Okay, so let's talk a bit about how we construct a truth table. We'll construct a couple of them, and then we'll jump into giving some definitions related to this notion of truth. So let's suppose we have a complex sentence S that was constructed from a collection of n atomic sentences. And let's call those atomic sentences, say, A1 through AN. And again, what this means is that you then followed the rules for constructing, things like the conjunction, disjunction, and negation, putting these atomic sentences together over and over with these disjunction and conjunction symbols to produce this sentence S. Now, to build a truth table for S, you begin by writing the atomic sentences one by one on the top row of a table. And then you place the sentence S to the right of all of those in that same top row. You'll be introducing several other rows in your truth table, but it's customary to draw a double line separating the atomic sentence from the sentence S all the way on the right. Now, it's not necessary, but the book follows that convention, and we'll try to stick to that convention as well. Now, the truth table tries to explore all the possible ways of assigning true and false to those atomic sentences. And again, in this instance, there are n of them. So there's A1 through AN. And what you'll do is you'll fill out the rows of this table underneath A1 through AN, writing down all of the various possibilities for these truth assignments. Now, there's two choices for A1, either true or false. There's two choices for A2, true or false, and so on and so forth, all the way to you get to AN. Multiplying those all together, you get 2 to the n possible choices for assigning true or false to those atomic sentences. And what that means is that if you have n atomic sentences in your complex sentence S, then the truth table that you construct is going to require 2 to the n rows. So 2 atomic sentences means that you have 4 rows, and 3 atomic sentences means that you have 8 rows, and so on and so forth. Let's jump into a pretty straightforward and simple example. And this example has a complex sentence S, which has 2 atomic sentences in it. However, those atomic sentences are identical. They're both cube A. So the first thing that we would do is just write down that atomic sentence in the first row of our truth table. And so you can see it up there on the top as cube A. Now, because there's only one atomic sentence appearing in this complex sentence, the number of rows that we're going to have in our truth table is going to be 2 to the power of 1, which is just 2. And that's because there's only 2 possibilities for this atomic sentence, cube A. Either it's true or it's false. Then to the right of those atomic sentences, we write the complex sentence S, which in this case is cube A or negation cube A. And you'll notice that we put a double vertical line there to indicate that we're separating those atomic sentences from the complex sentence that we're interested in investigating the truth value of. Now, the textbook follows the method of basically going through and evaluating the various connectives that you're seeing one by one. For example, on the second line, you'll notice that there is an F and a T, but they've been written directly below the negation connective. And you'll notice that that connective is attached directly to the atomic sentence cube A. And so right under that connective, what we're doing or what we're indicating is just that the truth values are switching from true to false and false to true. So now in the first row, we get an F, and in the second row, we get a T. And that has to do with how we filled out the rows for cube A. They just have to swap. Then on the third line down, we evaluate that second logical connective using, again, the truth table back from our previous chapter when we introduced the notion of a disjunction. Now, remember that a disjunction is false when both disjuncts are false and true in all other possible circumstances. So here we would look at cube A and negation of cube A, and both pieces of information for that are given back on that second line. So in the first row, cube A is true and negation cube A is false, so therefore their disjunction has to be true. On the second line, cube A is false and the negation of cube A is true, and therefore their disjunction is true. And you can see that that T and a T has been written directly below that disjunction. Now that's the primary connective for that complex sentence. And what I mean by primary connective there is it's the sort of last one that was used in the construction of this sentence. And therefore it's the one that tells us the actual truth value of this particular sentence. And so we can see here that this sentence, cube A or not cube A, is true in all possible circumstances. And that should make some sense because in English it says that either A is a cube or it's not a cube. And those are the only 2 possibilities. So now let's go on to a slightly more complicated example where we have multiple atomic sentences appearing. In this case, we'll analyze the sentence cube A and cube B or negation cube C. In other words, either A and B are cubes or C is not a cube. There are 3 connective symbols here, conjunction, a disjunction, and a negation, and there are 3 atomic sentences, cube A, cube B, and cube C. Now, what that means is that when we construct our truth table, there's going to be 2 to the power of 3, or 8 different rows that we'll have to consider. And the number of rows that we consider, or what we put in those rows, are all the possible different ways of evaluating these 3 atomic sentences as either being true or false. You're also seeing a convention here that is helpful for making it a bit more manageable and easy to recognize the pieces. We will often replace atomic sentences with just capital letters. And so in this case, cube A has been replaced with just capital A. Cube B has been replaced with capital B. and cube C has been replaced with capital C. And therefore, the complex sentence that we were interested in was really the sentence A and B or negation C. And you can see the first step in constructing the truth table for this down below. We've, on that first row, put down those atomic sentences A, B, and C. Then we have a double vertical bar and the complex sentence we're interested in investigating. Then below A, B, and C, we go through all the possible different truth values for those sentences. And it's easiest when you have 8 different possibilities to, in the first column, put 4 T's and then 4 F's. And then in the second column, you can do 2 T's, 2 F's, 2 T's, 2 F's. And then finally, in the last column, you repeat the pattern TF, TF, TF all the way down. And that'll give you all the different possible ways of making these atomic sentences true. Now, in the next step, what we'll do is start evaluating those various connectives that we're seeing. And there's going to be 3 connectives here. So we'll have to evaluate all 3 of those as we go through to determine the truth values of this complex sentence. So the first connectives that we'll evaluate are those that are the ones most closely connected to those atomic sentences. So that's the conjunction there highlighted in blue, and then also the negation of C over there on the right. Let's focus in here first on evaluating that conjunction of A and B. And to evaluate that conjunction of A and B, you really only need to focus on the 2 columns for A and B, because that's the only information that's going to be needed to determine the truth value of the conjunction of A and B. And remember, that's because of the truth functional nature of the conjunction connective. Now, I'll remind you that the conjunction is true in only one circumstance, and that's precisely when both of the conjuncts are true. In this case, when both A and B are true. And I've highlighted the 2 rows where that's the case, the first row and the second row. You'll notice that all the remaining rows that you see here have a possibility of either true and false, false and true, or just false and false. Now, the reason why I highlighted those rows in yellow is that those are the rows that I'll mark the conjunction as true. And then I know that I don't even have to really check what's going on in the other rows. Those are the only places where it's true, and so everything else will be marked as F. And you can see that in the remaining rows for that conjunction. So again, don't forget that in conjunction, if you can figure out the places where you have a T, that's a very specific thing, then everything else has to be an F, and you don't have to analyze it piece by piece. Next, we can focus on the negation connective that is attached to the atomic sentence C. This one's really pretty straightforward to evaluate because you just have to focus on the column for the atomic sentence C. And recall that the semantics for negation is that it just basically switches the truth value. So any T's become F's, any F's become T. Now we can focus on evaluating the primary connective of our complex sentence. And that was the last one that was used in its construction. That's the disjunction symbol that I've highlighted here. And the 2 disjuncts are A conjunction B and negation C. And so I've highlighted those 2 columns as well, because those are the 2 columns that we'll need to evaluate that disjunction using the semantics that we defined for it using truth tables back in the previous chapter. Now, the easiest way to fill out a disjunction like this is to first recall that the only way a disjunction can be false is if both disjuncts are false. So typically what I do when I fill out a table for something like a disjunction, I'll go through and highlight all of the rows where those two disjuncts are false. And you can see that happening here where I've highlighted in yellow. So that third row, the fifth row, and the seventh row have a value of F for both A conjunction B and negation C. And so those would be the three places that for the disjunction, that middle column that we're sort of filling out, those would be the three places where I would put an F. And then in all other instances, the disjunction comes out to be true. And so we can just put a T everywhere else. So again, for the conjunction, I find all of the places where it should be true, and then you get F's everywhere else. And for the disjunction, you find all of the places where it should be false, and then you put T's everywhere else. And again, what we're seeing here are all the different possible truth values for our complex sentence that was built up of these three atomic sentences. So now that we've introduced the notion of a truth table for a complex sentence, we can start talking about a bit of terminology that is related to logical necessity and logical possibility. And the idea is perhaps best understood as being a stricter version of logical truth. The word that we'll use is tautology. And a sentence will be a tautology if it has only T's in the column under its main connective. And because of the truth functional nature of these complex sentences, what that means is that that sentence will be true in all possible circumstances. In other words, it's a logical truth. On the other hand, there are some logical truths that are not tautologies. And we'll sometimes also refer to these sentences that are tautologies as TT necessary or truth table necessary. And we'll also introduce the corresponding notion of TT possible, truth table possible, meaning there's some row where the sentence comes out as true. Now, down below, you can see one of the sentences that we evaluated, cube A or not cube A. And in regular old English, that would be either A is a cube or it's not a cube. And then a second sentence built up from the atomic sentences A, B, and C that's analyzed in the textbook. And I think that's a really good analysis. And so if you haven't already sort of looked through that particular analysis, you should look through it and check out that truth table. But when we constructed the truth table for that first sentence there, the one with cube A in it, we found that we always got T's. And so it was an example of a tautology and therefore a logical truth. And we would also say that it's TT necessary. And likewise, the same thing is true of the sentence on the right there, A, B, and C. It is also going to get T's underneath it if you go through that process of evaluating that truth table. And so it is also a tautology as well. And you'll notice that we don't even really need to know what those underlying atomic sentences A, B, and C are, just that the Boolean connectives we used were truth functional in nature. Okay, so just a quick emphasis of what I said about tautologies. Recall that something that's logically necessary is called a logical truth, and it's true in all possible circumstances. So in that regard, all tautologies are logically necessary. In other words, they're logical truths. On the other hand, there are some logically necessary sentences, or in other words, logical truths, that are not tautologies. And a really excellent example of this is something that we've already talked about that's based on the indiscernibility of identicals. And remember that indiscernibility of identicals told us that we could introduce sentences like A is equal to A for any complex terms that we would like. And in any first order language, such a sentence would be true. So that rule in our deductive system was called equality introduction. And therefore, that's logically necessary. On the other hand, notice that on its own, A equals A is just simply an atomic sentence. There are no connectives, Boolean connectives, being used here. And so if we were to construct a truth table for this particular atomic sentence, it would be really simple. It would just be two rows, and it would be a T and an F. However, notice that one of the rows is not a possibility. The fact is A equals A is always true, and therefore it's a logical truth or logically necessary. But that truth, that logical truth, wouldn't be picked up in a truth table. And there are lots and lots of facts like this that are related to this indiscernibility of identicals that lead to logically necessary statements that are not tautologies. Remember, the tautology is sort of being built up from that truth functional sort of aspect of the connectives. The textbook offers a fantastic Venn diagram explaining the connections between tautologies, logical necessities, and TW necessities, or Tarski world necessities. And I've tried to highlight those here in yellow, green, and blue. And we should sort of think about the strongest of these sort of logical truths, or the strictest of them, as being these tautologies, the sort of complex sentences where the truth table arrives at a T in all instances, and they are true just from the truth functional nature of the connectives and don't really have anything to do with the meaning of any of the predicates or the truth values of the underlying atomic sentences. So those are examples of logical truths, but they're called tautologies. And so they would be contained within the collection of logical necessities, right? So that's why we have there sort of that inner circle, then followed by that sort of nebulous circle there for logical necessity. And the reason it sort of looks nebulous in this picture here and it's not well defined is that it's sort of vague, right? What did we mean by possible circumstances? Now, on the other hand, tautologies are very strong, and it's clear what the definition is for a tautology. And likewise, a Tarski's world necessity is also clearly defined in terms of the Tarski's world program. However, the logical necessity here is what we're trying to sort of hone in on, and you can see that we're sort of squeezing in on logical truth there. But let's go through and just analyze each of these highlighted sentences here one by one. The first one there in yellow all the way in the middle. And before I do that, let me just mention that there's several homework assignments where you'll be constructing, Venn diagrams like this, and then also trying to put various atomic sentences and complex sentences somewhere in this particular Venn diagram. So ideally that helps you with this sort of setup. Okay, so that first one on the inside there is tet A or not tet A, and that, if you filled out the truth table, would give you nothing but T's, so it's a tautology. And it says that A is either a tetrahedron or it's not. So clearly it's a logical sort of truth, but it's a very strict and strong one. It's a tautology. And then we have a couple of sentences here that are logical necessities, but not tautologies. And those are the ones that are highlighted in green. The first one there says the negation of, so it's not the case that, larger AB and, or conjunction, larger BA. So it's never the case that A is larger than B and B is larger than A. So that's not a possibility. And you can sort of imagine that, there's just no way for that particular sentence to be false. Another example is a conjunction of sort of the or of a sentence that we saw on the previous slide. So here we have A equals A, and then also B equals B. And since both of those statements are true, their conjunction then has to be true as well. On the other hand, if you were to construct the truth tables for these sentences, based all the way through their atomic sentences, then you would find that there are some instances or some combinations of T and F that make this particular statement false. So in this case, they would be logical necessities, but not tautologies. Okay, and then sitting on the other side of the logical necessities are sentences like the following: tet A or cube A or dodec A. And as we said sort of in a previous slide, if we're willing to consider worlds beyond Tarski's world, where maybe the shapes have things like spheres or other sort of shapes that we're not considering, then this particular sentence could be false. Okay, so it would not be logically necessary. The same thing for the sentence small b or medium b or large b, because we can imagine a world outside of the Tarski's world program where we allow for shapes that are bigger than those that might be called large in Tarski's world, or might even have 3 different designations of sizes. So that particular sentence could be false in some possible circumstance. On the other hand, notice that it's within the circle that says it's a Tarski's world necessity, because there is no way we could construct a world in Tarski's world program, the program Tarski's world, that would make these sentences false. For example, the first one, if A is a term, if A is a constant here that names some sort of object on the board, then that object is either going to be a tetrahedron, a cube, or a dodecahedron. And so that sentence would be true. And likewise, for the second sentence, if you have some constant naming an object, in this case, that constant being B, then that object is either going to be small, medium, or large in Tarski's world. And so that sentence would effectively be true as well. So these would be Tarski's world necessities that are not logical necessities. And then finally, the sentence up there on the top, cube A and large AB, is an example of something that could possibly be true or possibly be false in Tarski's world. And this was sort of a question from a previous quiz. I think it went along the lines of, is it possible for some sentence to be true in some circumstances and false in other circumstances? And here's an example, right? So we could build a Tarski's world where it's true in a place where it's false, and therefore we would say that it's not Tarski's world necessary. On the other hand, it would be Tarski's world possible, because you could certainly build a world with 2 blocks in it, named A and B, with A being a cube and A being larger than B. Okay, so you'll be tasked in the homework exercises with constructing a similar Venn diagram for the notion of possibility. So let's remind ourselves of those. I think I've mentioned them a little bit, but let's say it one more time so you have a reminder of that, and then point out a couple of sentences related to these definitions. So we'll say that a sentence P is truth table possible, or TT possible, if it's true in at least one row of its truth table. In other words, the column that's associated to P in that truth table has a T somewhere in it. And then there's some possible circumstance on the truth table when it's true. So we would say it's TT possible. And then we say a sentence P in the blocks language, and it has to be in the blocks language here, is Tarski's world possible, or TW possible, if it's true in some world that can be built in the program Tarski's world. Um, and again, we were saying that these are more precise notions of what we mean by possible circumstances and the imprecise notion of logical possibility. Okay, so we have two examples here. One is from our previous diagram. That was that sentence out there on the top. Notice that it has two atomic sentences, cube A and larger AB. And so if we were to construct a truth table for it, it would have four rows. And in particular, there would be a row where cube A was true and large AB was true. Larger AB was true. And so their conjunction would be true. So that sentence, I put a little pink check mark there to indicate that it's truth table possible. On the other hand, as I said in the previous slide, you could construct a world in Tarski's world where A is a cube and A is larger than whatever B names. And so this would be also TW possible. So I put a little check there as well. Now, back when we were sort of analyzing necessity a bit, we ran into this sentence, the negation of tet B or cube B or dodec B, that disjunction. And we found that it was impossible to build a world in the program Tarski's world that made this particular sentence true. And that's because no matter how hard we sort of move around B, it either has to be a tetrahedron, a cube, or a dodecahedron. That's all there is in that program Tarski's world. And so the negation would certainly make it false. So this thing would not be TW possible. On the other hand, if you construct its truth table, it would have three atomic sentences, so 2 to the power of 3, or 8 possible rows. And in any row where one of those atomic sentences was true, the disjunction would be true, and then the negation would be false. On the other hand, if you had a row where all of those statements were false, and that would happen in a truth table, even though it couldn't possibly happen in Tarski's world. But if you had a row where all of those were false, then the disjunction would be false and the negation would be true. And so this sentence would actually be truth table possible. But again, this is just a bit of an analysis to help you get started with that homework exercise where you're constructing your own Venn diagram. Okay, so let's just take a little bit of a detour here and say a bit about truth functional connectives and the fact that there are also functional connectives that are not truth functional in nature. And the book doesn't really call them out as modal logic, but I'll just point out that if you're interested, you can do a quick Google search and you'll find the idea of modal logic, which extends first order logic with two connectives that are not truth functional in nature. We won't include those in our setup, but let me just point out how they're not truth functional in nature. The first is related to the idea of possibility. In other words, it is possible that, and then you say a sentence. And the second is related to this idea of necessity. And what you say is, it is necessarily the case that, and then you place a sentence. Now, in modal logic, the symbols that you would use are diamond and box. And so the fact that the sentence P is possible is denoted by diamond P, and the fact that it would be necessary would be denoted by box P. And box P always implies diamond P. But notice that these are not truth functional in nature. And what I mean by that is if you were to replace P with some atomic sentence, for example, in the blocks language, let's just say P was something like tet A. In other words, A is a tetrahedron. Well, then it's not enough to know the truth value of that statement, tet A, to determine if diamond tet A or box tet A is true. Because in those two instances, you'd have to examine all possible worlds and all the different sort of truth values that you would have in order to do that. And so these would be examples of logical connectives that are not truth functional in nature. And my point here of bringing them up is just that they're interesting because we're sort of bringing up these definitions in our previous slides here, and they are interesting concepts, but they are not the type of connective like a conjunction or a disjunction or a negation that just depends on the underlying truth value of that sentence P. Okay, so now let's come back to our notion of logical equivalence. Remember that when we were judging our English translations of first order sentences, we said the only criteria that we really had for a good translation was not anything grammatical or stylistic about the English sentence, but instead that it has the same truth value in all possible circumstances. In other words, that the sentence is logically equivalent to the first order one. And this is a very nice notion, and it's fairly interesting. However, it's a bit vague. And the vagueness, again, comes in because of this notion of what it means to be a possible circumstance. Now, we've now sort of made it a bit more concrete what we mean by some possible circumstances. So let's also introduce some other versions of equivalence as well. So one possible instantiation of these circumstances is, again, the notion of truth tables. And we'll say that two sentences are tautologically equivalent if they can be seen to be equivalent simply by virtue of the meanings of their truth functional connectives. Now, in terms of truth tables, it's actually a pretty straightforward process to determine if two sentences are tautologically equivalent. What you do is you construct a joint truth table. So a truth table not just for one sentence, say S, but also the second sentence that you'd like to check its tautological equivalence with. And once you've constructed that joint table that has all the possible truth values for the underlying atomic sentences for both of your two sentences, you can check to see if the two columns for your sentences are identical. Now, if they're identical in the truth table, then they're always going to give you the same truth values based on the underlying truth functional connectives, even though the complex sentences may look very different from one another. And so in this instance, when they have the same columns in your truth table, you say that your two sentences are tautologically equivalent. Now, just to be clear, all tautological equivalences are definitely logical equivalences. However, there are some logical equivalences that are not tautological. And a really good example of that is given in the textbook, and I've recreated it down here on the bottom of the slide. There are two sentences. First, we have A equals B, conjunction cube A. The second is A equals B, conjunction cube B. Now, by the indiscernibility of identicals, because we know that A is equal to B is true in both of those sentences, if we assume those sentences are true, then that second conjunct has to have the same truth value as well. So if cube A is true, then cube B will be true because we can substitute A for B. And vice versa, if cube A is false, then cube B would be false as well. And so these two sentences together have the same truth values in all possible circumstances. So they are logically equivalent. However, you should notice that they are not tautologically equivalent to one another. Notice if you were to construct a joint truth table, you have three underlying atomic sentences. A equals B, cube A, and cube B. This means there would be 8 rows in that particular truth table. And there would be a row where A equals B is true, cube A is marked as true, but cube B would be marked as false. And that's because, again, in a truth table, we don't really think much or consider the meaning of the underlying predicates in our atomic sentences. We simply list off all the possibilities, even if some of those possibilities are not logically possible. For instance, A equals B being true, with cube A being true and cube B being false. And that's because it would violate that indiscernibility of identicals that we had talked about for that equality relation or that equality predicate, which is in every possible first order language. So again, some logical equivalences are not tautological equivalences. So we can also refine the notion of consequence. And we can think of tautological consequence as being a stricter form of logical consequence. So what do we mean? We say that a sentence Q is a tautological consequence of some premises P1 through Pn if every row in their joint truth table that assigns true to all the premises also assigns true to the sentence Q. So for example, here I have a truth table with underlying atomic sentences A, B, and C. So there are 8 rows. And then we have 3 complex sentences. Now, the first 2 are A disjunction negation B and B disjunction C. And we'll think about those as being our 2 premises of our argument. And then that column there that I've highlighted in blue, A disjunction C, we'll think about as being our conclusion. Now, when we fill out the joint truth table here, we get truth tables based on those connectives. And what I've highlighted here in green are all of the rows where those 2 premises, A disjunction negation B and B disjunction C, are both true. So those are the rows that we identify when we're looking to establish a tautological consequence. And if another sentence is a tautological consequences of these premises, then what we'll find is that when we construct the column associated to that sentence, we'll also get T's in these exact same rows. And you'll notice here that for that sentence, A disjunction C, we get T's in each one of those 4 highlighted green rows. And so therefore, we can think about that sentence as being a tautological consequence of those 2 premises. So the notion of tautological consequence is nicely built into our Fitch program. And it's obtained as a justification, or it looks just like a rule, even though it's not one of our, or is going to be one of our formal rules. And you can obtain it the same way that you used ANCON, or analytic consequence, in that same little table. It's denoted tautcon in Fitch. And again, it will require you to cite some sentences. So here I've highlighted those sentences there in red, same row AD, same row DF. And then the row that I'm trying to justify is that one there that has the little arrow, same row BC and same row AD. And when you pick tautological consequence, what Fitch will do behind the scenes is basically construct a truth table or a joint truth table for all of those sentences. And then it'll look in the rows where the premises or the cited sentences are true and see if the sentence you're trying to justify is also true in those circumstances as well. And if it's always the case that it's true, whenever the premises are marked true in a truth table, then you'll get a little check mark there and you can be assured that you have a tautological consequence. Now, when there's lots of atomic sentences floating around in the blocks language and this sort of thing, it can be hard to see how the underlying truth tables are going to be built up, especially when you're looking at this in Fitch. And one nice feature is these little goggles that you'll see on the side. So when you click TopCon as your justification, you'll see a pair of goggles there on the side in that same row. And if you click on it, what it does is it sort of redacts the atomic sentences, and it redacts them with the same color. So for example, that same row AD gets redacted with a green, and then same row DF gets this sort of purple, and then same row BC gets this dark purple. And notice that it didn't redact that one on the top because it wasn't one of our highlighted premises. It's not one of the ones that we were considering. And so you can see here that this is not necessarily going to be a tautological consequence because it could be the case that that first conjunct, that one in dark purple, could be false if all we're doing is constructing a truth table there for those ones in red. But again, the underlying tautological consequence doesn't depend on the meaning of those atomic sentences, just on what happens in the truth table when you go through all possibilities for true and false. So the next two slides are intended to help you with the discussion for this week, where we talk a bit about normal forms. Now, when we're constructing a normal form for a complex sentence, we will utilize some tautological consequences in order to do that. The tautological consequences we looked at previously had been called just logical truths, but it turns out that all of the ones that we'll use in these constructions to get something into its normal form are actually tautological consequences. And so they can actually just be checked with the truth table. For example, when we are going to put some complex sentence into negation normal form, we'll always use De Morgan's laws. That's where we can sort of pass that negation through a conjunction, and it flips the conjunction to a disjunction or vice versa. And the double negation law, which says that two negations in a row sort of cancel each other out. Now, if you construct truth tables for those particular sentences, you'll find that those lead to not only tautological consequences, but that those sentences are tautologically equivalent. And here, this double arrow that you're seeing represents logical equivalence. But again, these are tautological equivalences as well. So they're a bit stronger than just a logical equivalence. Now, we'll use De Morgan's law and the negation laws. And there's an example here on the left. But before I talk through the example, we'll use those two laws to rewrite our sentence in a way where the negations have been pushed through all of the conjunctions and disjunctions all the way down to the atomic sentences, so that any of the negation symbols that appear right next to atomic sentences, and therefore we just have basically literals and then conjunctions and disjunctions of those. And a tautologically equivalent sentence is said to be in negation normal form if this is the case, right? If you've pushed those negations all the way down to the atomic sentences. Okay, so let's look at this example here that we see on the screen. And we're going to start with the left-hand side, which is not in negation normal form. That's primarily because there's this negation sort of all the way on the outside. And what we'll do is we'll use De Morgan's law first to pass that negation across the conjunction. And we'll get to that line there on the right-hand side of that first sort of double arrow. What we find is that we take the sort of negation to this A disjunction B, and then we take the negation to that negation C, so we end up with negation C, and then the conjunction flips to a disjunction. And again, what we're using there is De Morgan's law, which is a tautological equivalence or a tautological consequence. Next, we'll use double negation. So remember, double negation just says that two negations in a row cancel one another out. And so on that second line down, we replaced negation, negation C with just C. And again, that's because of, or you can do that because of the double negation law. Next, we applied De Morgan's law again, but now on sort of the simpler sentence of negation A disjunction B. And when we applied De Morgan's law, we get that negation A and the negation B, and then that disjunction flips to a conjunction. Now, remember, we're assuming here that A, B, and C are atomic sentences, and so we've pushed those negation symbols all the way down to those atomic sentences. Here we have negation A, negation B, and C. And so those are all literals. And this would be negation normal form for this particular sentence. So again, you use De Morgan's law and the double negation laws to push those negation symbols all the way down to the atomic sentences. So once we have a sentence in negation normal form, or NNF, we can proceed to then put it in either disjunctive normal form or conjunction normal form. Now, a sentence is said to be in DNF, or disjunctive normal form, if it's a disjunction of one or more conjunctions of literals. That's a bit of a mouthful, but it turns out that much like we use De Morgan's law and double negation law, here we can use the distributive laws for conjunction and disjunction to sort of rewrite them in this format, provided that we've already put them in negation normal form. Now, a sentence is in conjunction normal form if it's a conjunction of one or more disjunctions of literals. And again, we can just continue to apply what are called the distributive laws to move that negation normal form into either DNF or CNF, disjunction normal form or conjunction normal form. Now, the two distributive laws that we have for sentences are tautological equivalences, or in this case, tautological consequences as well. And what they say is that, for example, conjunction distributes over disjunction. That's that first line. And so if we have P conjunction Q disjunction R, then that's logically equivalent, and not only logically equivalent, but tautologically equivalent. You can check it with the truth table, to P and Q or P and R. And vice versa with the disjunction. You can distribute that over the conjunction. And the reason we use the words distributive law is that if we were to write the conjunction and disjunction instead with a multiplication and an addition symbol, this would be the familiar form for the distributive laws. Now, be a bit careful. The distributive laws also work from the other side as well. So that P could have been on the right-hand side of the Q or R. And you can still distribute from the right-hand side as well, just like you can do in everyday arithmetic. Okay, and down here we have a nice formula that's in disjunctive normal form. Notice that it's a disjunction of one or more conjunctions of literals. Here they're literals because they're just atomic sentences. There's no negations floating around at all. But the way in which we moved to this disjunctive normal form was to apply that first distributive law, that one which is labeled number one above. So let's see that in this context here. Let's start again with that left-hand side. We've got A or B, and then conjunction C or D. And the first thing that they do here is to distribute the A conjunction B, the A or B, across the C conjunction D. So here we will get A or B and C, and then a disjunction, A or B and D. And again, that's applying that first distributive law, distributing the A or B. So we're treating the P as the A or B. Now we apply the distributive law twice, but from the right-hand side. So we'll distribute first the C, and we get A and C or B and C. And so that's distributing the C. And then we get an OR, and we leave the A or B and D alone. And then finally, in that last line, we distribute the D across, and we get that A and D or B and D. And again, inside of the parentheses there, you have conjunctions of literals. There's no negations at all. They're just atomic sentences for those letters. So those are literals. And so you then have disjunctions of conjunctions. And if you wanted to put something in conjunctive normal form, you could then just use the other distribution law. And you could do that to this sentence as well. You could just continue to distribute that sentence, and you'd get back to something that was in that conjunctive normal form. Now, be a bit careful. If you've put something already into negation normal form, there may be some negations floating around. So this example doesn't have any negations. But remember that if you already put it into NNF form, those negations should be right up next to those atomic sentences. So these distributors' laws should work in the same way. No need to reapply De Morgan's law or the double negation laws. Okay. I hope you have a good time with the discussion this week, and I look forward to our next video.